Okay, so homework 3. Let's solve homework 3. Okay, so the first thing I'm going to want to do is I'm looking at where I have this set up, and I don't have my data file in the same directory as my markdown, right? So the first thing I'm going to want to do is fix that problem. So I have the data file. I posted it for you, right, on Slack, but I'm just going to copy and paste that data file into my homework directory so that it's in the same location as my markdown file, which will just make managing file locations a lot easier. Because by default, when it knits, it's going to look for files in the same directory that the markdown file is in. So if you keep everything in the same folder for a markdown, it will know to look for whatever files you're reading and writing. It'll look for them in the same directory as your markdown folder. So let's start with, doing well, how are you?
Good, thank you.
It is.
Oh, thank you.
Yeah. Have you been on the Slack and stuff?
No,
Okay.
this is my first time.
Okay, so let's touch base after class if that's good. I have office hours right after, unless you have something else.
Thank you.
Yeah. Okay, cool. Okay, so we're just reviewing last week's homework, but we'll catch you up at the end.
Thank you.
Okay, so I'm gonna read criminal, what's the file name? Criminal record.csv. Okay, and then I want to know how many cases are there in the data. So I want to do in row dat. I like to name my data dat just because it's easy to type, but you can name it whatever you want. And then I want to do summary dat, and how many cases is the tester black, and how many cases is the tester white. Okay. And then let's do table dat string black, I believe is the variable name. We can knit that real quick. Oh, right. What's my problem? Why did I get that error? See, it says line 47, error in read CSV, could not find function read CSV. Well, read.csv is one function. Read underscore is a different function that's in the tidyverse packages. And if it's in a package called readr, that actually is a little more efficient and it has slightly better behavior than read.csv for some really tedious things that you don't need to worry about. I did not load in my library. Okay. Yeah, it doesn't know where it is because I'm not, if I source it there, it's actually in a different working directory. But if I knit it, you'll see that the code runs, right? But you know, I also don't need all that tidyverse content, all those messages in my markdown. So what can I do? I could just have a new chunk right here where I run my libraries. And I'm going to say include equals F, right? So that it doesn't, so it'll run the code in the background, but it won't output the messages onto my document. I'm going to hit Command-Shift-K to knit. Okay, cool. It read in. It also gave me some messages on dat that I didn't really need. One thing I can do is I can suppress messages in particular. So I can say message equals F. So the tidyverse packages like to be really verbose. They like to tell us what they're doing, but we don't necessarily need that. I just want to read it in, and I don't need you to tell me what you read. Okay, but how many cases do we have? 696. Run a summary. Here's a summary of each variable. And run a table on the black variable, right, to get the race of the testers. And there we have it. So that's question 1. That was pretty straightforward, yeah? Okay. Now there is a little complexity in terms of reading it. Like if I hit play here, which is often what we want to do to make sure our code runs, it doesn't work, right? And the reason it doesn't work is because my working directory is right now set to be intro stats and not homework, which is where my markdown file is and where the data file is. So one way I can fix that is just in the console, I can set WD just to set my environment to have a working directory that matches my homework. So what I'm going to do is I'm going to set WD./HW, and it'll just set it to the current directory the subdirectory homework within the current location. If I use the dot, it'll say start where you are, but then go to the homework folder. Now, if I type get WD, I'm going to be in my homework folder, and this will run. So the problem with not being able to locate the file there was that my environment's working directory was different than the working directory I get when I knit my markdown document. So get WD is a command you can use to check your working directory to ensure that you're in the place that you need to be to read the files you need to read. Okay. Sorry, this is like a bit out of left field if you haven't seen this before. We'll get it, and all the lectures have been recorded, so you can go back and see the old lectures. Okay, so question 2, calculate the proportion of callbacks for white applicants without a criminal record and calculate this proportion for black applicants with and without a criminal record. Okay, anyone want to offer how you solved this problem? Right? This is actually incredibly simple. All we need to do is group by the 2 variables of interest and then compute the mean callback rate. Right? That's it. And we might want to save this as an object so we can work with it later. So let's call this results. Okay, but now in results, we have this. And from here, we can actually just do simple subtraction to compute the sample average treatment effect, right? The sample average treatment effect for black people with a criminal record relative to no criminal record, right, is 0.058 or 0.051 rather, minus 0.14. So you get like a negative 0.09, right? For white testers, it's 0.167 minus 0.34, so you get about a negative 0.17 effect for white testers. So for both groups, we see a negative impact of a criminal record on employment outcomes, right? That's the core of the study right there. So computing causal effects, if you've designed a randomized control trial, is actually just subtraction, right? That's all it is subtract out the outcome for the treatment group from the outcome for the control group. That's the sample average treatment effect. Okay. So now we want to compute the differences. I just did that in my head, but I want to do it for real now, right? So what we can do is we could do results group by black, and then it takes effects equals callback. No, it's a diff. I'm trying to be fancy here. I don't need to be fancy. Well, all we can do is we could say, okay, so we'll say results filter black equals 1. So we'll call this black results. Okay. So there we have that table, right? And then we can say from there, black results bracket 2, which we know is the treatment. Yeah, so black results we want to take. Let's do it with a filter. Let's do let's call it BR treatments, black results filter, primrec equals 1, select callback. Oh, it's still groups. An important thing to do with grouping is ungrouping at the end. Sometimes it changes the behavior of your data frames if you don't ungroup. So you can see here, it refused to drop the black variable because that's a grouping variable. So if I explicitly ungroup it though, then it will remove that structure from the data frame and it won't have a problem with dropping that variable. Okay, so let's look at BR treatment. There it is. Okay, so that's our treatment. And then we could do BR control. There are more efficient ways to do this, but I think this is, pretty easy to read relatively. So we'll take black results. We'll filter crim rec equals what? Because we're going to get our control. 0, because the control group is those without a criminal record. Select callback. And then we could do the effect is BR treatment minus BR control. Now you could obviously just do this by hand, and that's fine. It helps to spell things correctly. There we go. That's the causal effect for black subjects. Minus 0.09, right? About a 9-point gap, 9% lower callback rate. Then we could do the same thing here for white. I'm just going to copy and paste that block of code. Because what I can do is I can select all this, and then I can hit Command F, and I can say black results. Let's do black underscore, because I have black results and black control. Oh, no. Okay. BR. I'm going to replace that with WR, right? So I'm going to make it white results instead of black results here. I'll replace all in this code block. R studio, if I do a find and replace all, it'll do it only within the selection of what I've selected with my cursor if this box is ticked. So it's a quick way to modify your code. Here I want to do filter black not equal to 1. And then I want to call this white results. White results. I could have done a find and replace with this too. But a lot of times if I'm making code to do the same thing, just copying and pasting the code and then doing a find replace to switch out the variables or the different conditions that you need to switch out is really efficient rather than typing the whole thing again. Okay, and there's our effect for white respondents. We just wrote 20 lines of code to do subtraction, but that's okay. It's good practice, right? If you did it by hand, that's fine, right? As long as you understood, we're going to difference out the treatment minus the control to get the causal effect of the treatment. You wanted to have a negative number here because the causal effect of the treatment is to decrease the callback rate, right? So we were after a negative result. Okay. And then I think I asked you to compute differences and ratios. So once we have that, so we have the differences there, WR treatment minus WR control. So we could think about what is the proportion difference though? How much more likely is one group than the other? What percentage more likely is one group than the other? And that's going to be as a ratio. So we could do WR treatment over WR control. Right, and so for white respondents, people with criminal records have a 49%, 1 minus that, right? So let's do a 1 minus. 51%, they're 51% less likely to get a callback than are their peers with no criminal records, right? So effectively what we're doing there is asking how much smaller proportionally is the treatment group compared to the control group, right? So 1 minus the ratio will get us that. And if you didn't do a 1 minus, that's okay, right? But I wanted you to compute a ratio, and the difference from 1 will give us the kind of magnitude change, right? Because 1 is just equality. So we want to know the difference BR treatment over. So for black respondents, we get that, right? We get there's a that black respondents with criminal records are 64% less likely to get a callback than their peers. So even though the magnitude difference for black respondents was 0.09, the initial callback rate was lower, right? So the magnitude of change relative to where they started is actually higher for Black respondents when we compute it as a ratio, as a rate of change relative to where it started, rather than just a simple point difference. That subtlety may not kind of click right away, but that's important, right? Because they're starting in different places. When we look at the results, right, we can see the initial callback rate for Black respondents with no criminal record is only 0.14. So there's already a discrimination effect, right, of a 20-point gap between white and Black respondents with no criminal record. The key finding for this study, the headline, was that white testers with a criminal record had a higher callback rate than Black testers with no criminal record, right? So that but Black testers with a criminal record basically never got called back, right? But here we can see that if we divide, right, 0.14 by 0.05, right, we can see this is about double, right? But this is about 3 times higher. So that magnitude of difference in terms of proportional change is much higher for Black respondents than white respondents, even though this scale makes it look like this is a smaller effect than this, right? So it depends on like where our point of reference is, right, to determine the size of the effect. Proportional change versus absolute change. Yeah. Yeah.
I'm using group 5 for 2 different. So
Yep.
because I just like ended up making really complicated.
Neither stupid, definitely not stupid. Complicated, yes, but not stupid.
So they don't need like that.
Nope. Group by is really powerful. It takes a lot of things in base R that are incredibly complicated and makes them very simple. So you can group by any number of variables. So for example, let's look at that again. Let's say I also wanted to group by whether the job was in the city. I can do that, right? I just add a third variable. And now results is grouped by all 3. So now I have 1 row for a so for whether the job application was in the city, I have missing values here. So that's kind of throwing off the structure of the table. But I've grouped by 1, 2, 3 categorical variables, right? Each of which is binary. So I'm going to get 2 times 2 times 2 rows theoretically, except for the missings. So I'm adding 2 there as well. Anyway, yeah, you can group by 10 variables if you have them. And if that's interesting to you. Cool. Any other questions about that group by summarize piece? Okay. So compare the callback. We just did that. And we'll say, wow, that's messed up. Okay. And then, so yeah, when we looked at we didn't actually need to compute anything for question 4. We just needed to look at the relative callback rates. And, you know, compare this cell, or rather this cell to this cell, right? We just wanted to compare lines 2 and 3. And that's all I was asking you to do in question 4. And just kind of explain what that means in terms of the data. So if you came up with something like white testers with a criminal record had higher callback rates than Black testers without a criminal record, that's what we were after, right? Okay, now the external validity question, what did y'all think about this? Question 5, this was like no math, just think about it. So question 5, do we think we would see the same thing if we ran this study somewhere else? So we saw in Milwaukee, right, that in Milwaukee, with a study designed as she designed it, where we have matched pairs of subjects, right, where like the resumes are identical, the dress between the applicants is identical, they're wearing the same clothes, they're the same height, they're roughly the same weight, right, they're both well groomed, right? You could read the study in detail to get all that information about how she did the matching, and it's pretty rigorous, right? I think it'd be hard to argue with. She matched them as carefully as you could, such that the only thing really different between these two testers was their race, right? Or their perceived race. So what did y'all say about this?
It has to be yes, that there would be, like, otherwise that would be required. Every set of hiring managers across the country, across time, literally. So, yes, like it would, different results in places. Question would be like, is it similar, over different. I was like very interested in the specific conviction that she chose, thinking about if it had been specifically at that time, specifically compared to now, like what drug convictions, like socially, the way a hiring manager might make decisions might be different, visualize whether white collar crime versus drug offense or violent offense, like what business would like what does this mean about the person and their professionalism or professional so I think it would be different, but the question is like if differently if it's still
Yeah. No, I think that's, I mean, these are all great. Like this particular finding, those numbers are pretty darn close to each other, right? And they're actually, we'll talk about standard errors later, but they're within a standard deviation or two of each other. So this one may not replicate in other settings, like in terms of this number coming out higher than this number. But this number being higher than this number, I'm positive this would replicate in other settings, right? Now, so there are some like, and you'll get a sense for this as we go, of kind of like, how precisely is this measured? How much do I trust this study? How much do I think Milwaukee is really different than other places? Or like, maybe we're in a place where there's a really tight labor market, and so employers may not discriminate as much right now as they would at other times, right? Maybe this is also a function of like the relative unemployment rate in a place, and so how desperate are employers to find employees, right? That could also impact how much discrimination occurs in the market. So there's a lot of things that could be going on here. So when we think about a study like this, we don't want to say, we want to be cautious in how we extend it to other cases, right? External validity is the question of how valid is this study for external circumstances. Internal validity is the question of how valid is this study on its own circumstances. Did they design appropriately to answer the question they asked in the setting they asked it? External validity is, can we apply the findings of this study to other contexts, right? And external validity is hard in experimental settings. It's really hard. There are a lot of things that can threaten external validity. And it's one reason that a lot of people who study things like criminal justice or development economics or psychology or other things are really cautious about extending experimental findings to other settings, because people are really different and institutions are really different. And it can be hard to know exactly what those impacts are going to be across contexts without explicitly testing it, right? Like psychology, have y'all heard much of the debate about the validity of the psychology literature? Like one key threat to the external validity of psychology is that basically all of the study participants in most psychological experiments are undergrads at elite universities. They're mostly white. They're almost all affluent, right? So we have the whole base of like what we know in US-based psychology is largely built on undergrads enrolled in psych classes who are required to participate in psych experiments for course credit, right? That's like not good for external validity. That's horrible for external validity for lots of reasons, right? So like among this population, sure, what you found may be true. Among the population of undergrads enrolled in psychology classes at Yale, sure, your finding might hold. Among humans, that's a really distinct subset, and I would be really unwilling to generalize from undergrads enrolled in psychology classes at Yale to all of humanity, right? Anyway, that's my rant about methods in psychology. For today, you'll get more of them throughout the semester. And don't get me started on econ. Okay, so that's homework 3. I will upload this as a solution file later today. Any questions before we dive into lecture? Cool. Let's do it. So if you want to follow along with the slides, 4 causal 2 is posted on slides. Today we're going to wrap up our conversation about the basics of causal inference. Obviously, there's a lot more to talk about here. There are entire classes you could take just on causal inference. Professor Apel teaches an advanced stats class on causal inference that if you're thinking about doing quantitative work that's really focused on identifying causal effects, I strongly recommend. He's great at this stuff, especially with using observational data. We're going to talk about a couple methods. So we've used experimental data already. Today, we're going to introduce methods that can be used to identify causal effects in non-experimental settings. That is, where we have not designed an experiment, where we have not manipulated anything. We're just using data that we observe from the real world. But in certain circumstances, in special circumstances, we can use that data to make a causal inference, right? So let's kind of first go back to Pager, though, and take what we think of RCTs, randomized controlled trials, are often described as the gold standard for causal evidence, right? Because we have complete control over the design of the study. We control who's in it. We control the manipulation. We control in terms of what treatment we deliver. We have full control over everything, right? We can make sure that only one thing is different between the treatment and control group, such that the only possible explanation for differences in outcomes is exposure to treatment, right? That's the perfect condition for identifying the causal effect. And so that's why randomized controlled trials are often called the gold standard for causal inference. There is a raging debate in the literature about how valid that assumption is. So don't take that as doctrine, but that's the general assumption in the field, is that randomized controlled trials are the gold standard for causal evidence. Again, there's a lot of reasons to say that that doesn't mean that RCTs are the only kind of evidence that we should consider when we're making decisions. Because there are strong limits to what RCTs can tell us, especially when it comes to external validity. Right? We've discussed a little bit about that. We'll kind of keep coming back to, that's more of a philosophy kind of question than a stats question, but we'll keep coming back to it. Okay, so the causal effect or the sample average treatment effect, the true causal effect, for observation I is equal to the callback for crim true minus callback for crim false for subject I, right? The true causal effect for one individual of a criminal record on their likelihood of getting a job is what would have happened for a callback for that individual if they had a criminal record, and what would have happened for that individual if they did not have a criminal record. The fundamental problem of causal inference is that we can never observe both outcomes. We can never observe the thing that did not happen, the counterfactual. We can only observe one because time exists, right? So if time didn't exist, cool, we could do all this, but time exists. So we can only observe either the subject was exposed to treatment or the subject was not exposed to treatment. We cannot observe both. So this is in kind of data frame format, right? What that looks like. We have this person did have a criminal, this is the callback outcome under the criminal record condition, but obviously we can't observe this individual under the did not have a criminal record condition, because this person did have a criminal record when they went for the interview or they applied for the job, right? And so the NAs represent the counterfactual that we did not observe, right? The numeric values represent the actual outcome we observed. Those are real data. The NAs are data we wish we had, but we don't. And never will be able to have, right? So a randomized controlled trial gets around this by randomizing assignment to treatment. By randomizing, we can treat units as equivalent. By randomizing who's in the treatment group who's in the control group. We can treat those units, we can treat those groups as indistinguishable. If we use a random number generator to say, you're in treatment, you're in control, you're in treatment, you're in control, what we do is we effectively erase differences between the groups. We effectively ensure that there are no systematic differences between the groups. We don't select on anything. All we allow to drive whether you're exposed to treatment or control is a random number, right? By doing that, we ensure that the treatment group and the control group are statistically identical. I don't say practically, empirically identical, because of course they're not going to be, right? There will be differences between the groups, but with a sufficiently large N, if we had 1 million, there would be virtually no differences between a group randomly assigned to treatment or control. With a sufficiently large N, the differences will flatten and they'll be indistinguishable. Yeah.
Yeah, I was gonna, last time we were talking about randomization, I had this question, but it seems kind of ridiculous. But with, like, when I know with randomized like assignment, you can obviously do like a cluster or some type of sampling that like that you have certain populations that you want in a sample. But if you just had like one group, but you're saying like with a big sample size, it wouldn't matter. If you had a smaller sample and you have one group that was not, you wanted to, like, let's say, include a certain amount of races in.
We're getting to a problem of statistical inference that is kind of like, how do we design surveys and how do we design population? The reason you might want to do something like stratifying or clustering is if you want to make inferences about a relatively small subgroup. And so to get enough statistical power to make those inferences, you need more of them in the sample. So you oversample that group. We're not going to cover that yet. That's something for like a survey design class because it gets complicated, but there are ways to preserve the logic of random sampling, even when we're not entirely being random, right? Even when we're sampling some groups deliberately, you can still preserve the logic of the random sample. Yeah, but here we're just going to take the really simple case, one population that we're interested in making inferences about, and then assignment to treatment and control. You'll notice in Pager's experiment, this actually comes up because she oversampled Black respondents, right? And part of the reason for that was she knew that the callback rate would be lower. And so to have enough statistical power to get reasonable uncertainty estimates, she needed more people in that group. She wanted higher precision for that group. So she included more in the sample, but that's neither here nor there. By randomizing assignment to treatment, we can treat units as equivalent. When we get to probability distributions, you'll start to see what I mean more by this. But effectively, we're saying if I have, an equal number, so there are things in populations we can observe and things in populations we cannot observe, right? There are things on individuals that could affect our outcome, right? So let's say we're gonna take a group of all Rutgers students and give them some study coaching, or let's take like all students who take statistics, and a treatment group is going to get 3 hours a week of extra programming coaching, and a control group is not, right? And we're going to randomly assign people into those groups, right? Now, let's stop there. Rather than randomly assigning, let's say we're concerned that first generation college students may have a harder time adjusting to statistics than non-first generation college students. So we're going to assign first generation college students to this group and non-first generation students to this other group. Would we be able to ascertain a causal effect of the intervention when we do that? The populations are systematically different, right? Why would someone be first generation college and why would someone be not first generation college? The things that differ between those groups are much greater than just having previously gone to college and not having previously gone to college, right? Probably geography and race and socioeconomic backgrounds, perhaps immigration status, right? All of these things are going to impact whether that student's parents went to college, right? And it's really going to be tough to know whether it was the intervention that improved their scores or whether we would have seen similar improvement without the intervention in that context. This is kind of, I'm not explaining this particularly well, but we'll keep going with it. And I have some examples I'll show you later. But the idea is we randomize, if we randomized exposure across the groups, in theory, we'd have an equal proportion of first generation students in the treatment group and the control group because everyone has the same chance of being exposed to treatment. If we've done it that way, then we can actually compare among first generation students, how much did those improve who got the treatment versus those that did not get the treatment, right? By randomizing, we ensure an equal proportion of people with the same characteristics across both groups with a sufficiently large n, right? Of course, with a small n, we could have random fluctuations that we have more in one group than another. We'll come back to that. So if units are equivalent, if the treatment and control group are identical, mathematically, right? If they're theoretically identical, there are no systematic differences between these groups. All we need to do is difference out the outcome for the treatment and control group, right? Because everything about these groups is identical, theoretically, except for their exposure to treatment, right? So we've satisfied mathematically what we need to satisfy to compute the causal effect if we randomize, and only if we randomize. Yeah.
So if you are not using data that set up as randomized, that would be then control for other variables in the back. Is that correct?
You will not get a causal effect that way.
Yeah, seems like impossible without.
You have to design for causal inference. Just running a regression where you add statistical controls in does not get you a causal effect. We'll talk more about that as we go. What that does is it compares averages across subgroups.
Yeah.
So it does tell us something, but it doesn't tell us causal effect. And we'll kind of, when we get to regression, I will harp on that endlessly because I think it's really important. And it's not to say that regression isn't useful, but we definitely over interpret regressions to have causal interpretations when they don't. So we'll talk about that. So if we don't randomize, which is the case of just having observational data and adding control variables, we have no assurance that the treated and control groups are equivalent. And that means we don't have a strong case that we've obtained the counterfactual, which is what we're after. What would have happened if this unit had not been treated? If we don't have any assurance that the two groups are equivalent, we can't treat the groups that didn't get the treatment if they selected, okay, so like who wants to get the vaccine and who doesn't? And then we'll compare mortality rates across those. We have no evidence base from that alone, right, that the treatment and control groups aren't systematically different in some other way. They self-selected into treatment. And we know, for example, people with higher levels of education, people who are more affluent, people with higher, there are clear demographic patterns to who's receiving the vaccine and who's not, right? So selecting into that, and that's partially a matter of choice of getting it, but it's also partially a matter of access, right? In terms of who is it available to. So when we select only on the choice to receive a treatment, we can't really identify a true causal effect between the treated and the untreated because the groups are not identical. We haven't observed. What we're after is the counterfactual. What would have happened to the treated group had they not been treated? But in this case, if we're talking about, selecting into a vaccine, the treated group and the untreated group are not identical, right? They are socially very different. Yeah.
You make plausible inferences from if the treatment is like an exogenous effect on a relatively identical group.
Let's back up. What do you mean by exogenous?
I mean, like something that you as a researcher are not applying the treatment.
Right.
You're looking at say, like randomly one day, like there was 80 criminal records wiped, from the employment database or something,
A natural experiment.
Yeah. So would that would be?
We're going to talk about that in a second. So that's a question of using observational data to obtain a causal inference. And yeah, we're going to come to that. We're going to talk about the difference in difference model that can answer that question if we have a natural experiment. If you hear the word exogenous, sorry, I don't mean to harp on it, but it's a weird like stats word that people probably haven't heard before. Exogenous means outside the system, right? So if you hear the word, it's spelled exogenous. And that means something from outside the system, right? Something from outside the causal system we're looking at. Something that kind of comes in from outside and has a causal effect on the thing we're interested in looking at. Exogenous is the opposite of endogenous. Endogenous means something within the system is driving the outcome, right? So something that is happening among the participants that is related to their, so you'll get into endogeneity and exogeneity when we start talking about can we identify causal effects, but exogeneity, meaning I don't really want to talk too much about that right now because we're going to get to it in a second, but I'm just going to write those words up on the board and we'll talk about exogeneity when we get to our next example. We're going to look at a minimum wage experiment and we'll talk about it there. Okay, so RCTs. Question on randomization. You all believe me at this point that randomization will yield two groups that are statistically indistinguishable. And then once we've done that, we can theoretically observe the counterfactual, right? We can theoretically observe what would have happened to the treated group if they weren't treated. That's what we're after. What would have happened to subject I if the thing that did happen didn't happen, right? We want to know the counterfactual. What would have happened in a different time if different conditions occurred, right? The only way we can do that under this framework is with randomization. Okay, so the sample average treatment effect is defined as the average of the difference of the outcome for the treated and the outcome for the control. So we just compute the average for each group and difference them, or compute the average of the differences. Same thing. That's the sample average treatment effect, is the average difference between the treated and controlled.
So when you were talking about the proportion you wanted in the homework, you were saying you would do 1 minus the treatment effect, basically?
If you wanted a proportional change
Yeah.
from the treated and controlled, yeah.
Okay, so just 1 minus the treatment effect.
Yeah. Because if it was greater, if the treatment group was higher than the control group, you, like, for example, maybe the treatment group had a callback rate of 0.5 and the control group had a callback rate of 0.4. If we divide 0.5 by 0.4, we get like what, 1.2 or 1.25. I can't actually do that math in my head very well because I'm not actually that great at math in my head. But which means you don't have to be either to do this stuff. That was the only point of that. But we get a positive number there. We get like maybe 1.25, but it hasn't increased by 125%. It's increased by 25%. So we want to subtract that from 1 to remove, the division by itself, right? So that way we get a 25% increase rather than a 125% increase. And if we difference it by 1, so if it were lower, if it were 0.3 rather than 0.4, right? 0.3 divided by 0.4 is whatever that is. And that's going to be like 0.7 something, right? But we don't want to say it's 72% is large. We want to say how much smaller is it? So we do a 1 minus, that's 0.72 to get 0.28. And we say it's 28% smaller, right? So that just gives us relative to the original quantity. Okay. That's why we do the 1 minus. Okay, so in practice, since we only observe yi1 or yi0, we instead estimate a difference in means of the outcome between the treatment and control, the mean of y1 minus the mean of y0, right? If assignment has been randomized, those values are identical. So we can still write the sample average treatment effect this way, but in practice, we're computing this. Okay, so why do we randomize? I'm going to introduce another experiment. This is from the EMI book. If you're following along, cool. You've seen this. If you're not, that's fine too. So this is an experiment on voting and social pressure. EMI is a political scientist, so a lot of the examples that I pull from the book are kind of about voting or other kind of political outcomes. But so this is the experiment. People received in the mail a mailer prior to a midterm election, and there were multiple possible messages they could have received. One would be a civic duty message. The whole point of democracy is that citizens are active participants in government, that we have a voice in government. Your voice starts with your vote. On August 8th, remember your rights and responsibilities as a citizen. Remember to vote. Do your civic duty, vote. That's the civic duty treatment. The Hawthorne effect is a hypothetical effect that might occur when people think they're being watched. So this one says, this year we're trying to figure out why people do or do not vote. We'll be studying voter turnout in the August 8th primary election. Our analysis will be based on public records, so you will not be contacted again or disturbed anyway. Anything we learn about your voting or not voting will remain confidential and will not be disclosed to anyone else. Do your civic duty, vote. This treatment implies to the voter that we will know if you vote or not. Right? That's the treatment, is letting the person know that someone is watching. Not that they're going to be disclosed to anybody, but there is someone. You will not be harmed. You will not be affected in any social way by this. It won't be disclosed, but just like the minimal possible surveillance, right? Like a researcher who won't disclose anything is studying the records and will know if you voted, right? So we have three possible treatments. We have three possible levels here. We have the civic duty message, the Hawthorne message, and nothing, right? So we have three groups of voters. Those who got the civic duty message, which was just like, voting is great, do it. This one that's like, I'm watching you. And this one that is like, just no letter was sent. Okay. And so we randomized who got which message. And we have a few different variables. So if you want to follow along, this is a URL you can use to download the data. It's in the slides if you want to just pull it there. I'm just going to start. One cool thing about R, so we can just like, if there's a CSV file on the web, we can just download it directly to the computer, right, with the URL. So that's how we're going to do that. And then here's the data. So if you run these two lines of code, you two will have the data in as social. So we have a few variables here. We have the voter sex. We have their year of birth. We have whether they voted in the 2004 primary. We have which treatment condition they received. We have whether they voted in the 2006 primary, which is the one that we're interested in measuring. We're measuring voting in 2006. This is an experiment conducted prior to the 2006 primary. And then we have the size of the respondent's household. Yeah? Okay. So, structure of the experiment, relatively clear. The data we collected, relatively clear. Cool. So let's take mean voting by treatment and control. So if we want to compute the control group, we'll take social. We're going to filter only those conditions where the messages is equal to control, right? Remember, messages is our kind of experimental column. So we're going to take only those who received the control, which is received no intervention. And we're going to compute the mean of primary 2006 to get the mean voting rate for the control group in the 2006 primary. We can see that it's 0.297. Then we want to compute the treatment. So those who received any message, we're not distinguishing between messages here. So they received either civic duty or Hawthorne. We're going to say filter messages not equal to control. Compute the mean there. We see a 0.338. Based on this, what can you infer? What's the sample average treatment effect? Right, so 0.338, the average for the treatment group minus the average for the control group. I did cut myself on that TV screen. Sorry. Wash my hands in a second. So 0.338 minus 0.297, it's about 4 points, 4 percentage points, 0.04, roughly, right? Everyone kind of clear on how we would compute the sample average treatment effect here? We've got the average for the treated group, the average for the control group, and then just take 0.338 minus 0.297. That's the sample average treatment effect. Yeah.
What, when you said that you use like
if the assignment has been randomized and values are identical, what did you mean with what not those two means, right?
No. What's identical is the average of yi1 minus yi0 is the same as the mean of y1 minus the mean of y0. This is differencing out each observation from the observed and the counterfactual, and then taking the average of that. This is just the mean of the treated and the controlled. And these are under randomization. These two quantities are equivalent. That's it. So that was just like, that's a proof. Don't worry too much about that. Okay, but this is, at the end of the day, all that we need to do. If we have data from a randomized control trial, we just compute the average for the treated group, the average for the control group, and we difference them. Subtract treatment minus the control average, and we have our sample average treatment effect. Okay, so the difference in means, treatment minus control, 0.04. Notice when I read a number like this, I'm not going to read 0.0416 blah, 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 right? Because like I don't actually trust my measurement that much. I'm just going to round it usually to 2 or 3 significant digits, right? A sort of good practice to get in is to not over-report decimals, right? Report usually no more than 2 or 3 decimals. Call this 0.04. We don't need to call this 0.042 or 0.0416, much less all that. Okay. Here's why randomization matters. So let's take voting proportion. So let's say, we know, for example, that voting differs across social groups, right? Different people are more likely to vote than others. So let's use year of birth as a way to compute how likely different groups are to vote. What do we see in this plot? We have year of birth on the x-axis. We have the proportion of people who voted in the 2006 primary on the y-axis. Who's most likely to vote by year of birth? Where is this peaked? Where about here? People born around like 1942. Boomers. They vote, right? Over 40% of them voted in the primary election in this range in 2006. Who's this? That's actually me, right? But this is like, people born in the mid to late 80s, right? How often are they voting? Like less than 15%. Less than 15% of them voted in that primary. This doesn't have anything to do with the treatment or control here, but we can see a really clear pattern to the data by age, right? Age clearly affects how likely people were to vote in the election. And the very old are also less likely, probably as a function of mobility and access, right? Getting to polling places is hard when you were born in 1905 and it's 2006, right? If you're 101, it's hard to get to the polling place without some help. And we see no voters in the sample who were, well, that's probably 2 people or 1 person. But I guess for it to be 0.33, that probably means we had 3 respondents and 1 of them voted and 2 of them didn't. But everyone kind of clear what the pattern is here? We have a kind of low voting rate at very high ages, high voting rate in kind of middle ages, low voting rate for very young eligible voters. Yeah?
So does this mean you want to equally sample people from each age range?
That's exactly what this means, is I want there to be an equal age distribution across my treatment and control. But I may not know this going into the study. There's all kinds of reasons why people do and don't vote, some of which I will know and can ask people, and then I can use that to inform my judgments. And those are called observable variables, and some of which I may have no idea about because no prior studies told me this is important, or maybe the weather in one neighborhood was really bad that day, and because we have segregation, it suppressed the vote turnout from one group more so than another, right? And the weather is certainly not something I included in my model, but we know weather drives vote turnout, right? So we want to randomize because we know some things are going to affect the distribution of the outcome, but there's also some things we don't know that will affect the distribution of the outcome. some things that are not measured or not measurable. Things we can't, there are some things we could measure if we had infinite resources. And then there are some things that we could never measure just because they're not possible to measure, but they still affect voting, right? Causal systems are really complicated. When we think about like, why does someone vote or not vote? We could probably list like 30 things right now that would affect someone's decision to vote, right? And that would be a short list. The list of actual factors that lead someone to vote or not vote could stretch back to like, what was their curriculum in first grade about civics or whatever, right? There's so many things that can impact someone's behavior, only a handful of which we can measure, right? Causal systems, that is all the things that feed into causing something to happen, are incredibly complex, right? And so in our studies and in our models, we're trying to simplify that as much as possible. That's why the randomized controlled trial is golden, because it can make sure that those things that we can observe and those things we can't observe are equal across groups, right? Randomization can do that. We're going to take 5, and I will come back, yeah, in 5. Keep going. And we'll start recording. Questions before we dive back in? We'll give people a minute to come back. No? It's kind of curious if it'll work through the rain. Like maybe rain is the condition where we get a quiet classroom. It probably would. Lightning will maybe shut it down.
This isn't what we're doing for this isn't the data set for homework, right?
No.
Okay.
This is just a demo data set that we're using right now.
Got it.
Just to do another, this is just a nice one because age is a really obvious thing that impacts voting behavior. And I can kind of talk about the distributional stuff for randomization. Yeah. Also, though, at this point, this is all like code that you more or less know, right? And you could make a plot that looks pretty nice, right? We'll do more plotting work as we go and more data visualization work as we go. But it's one thing I love about R is how easy it is to make really, really good looking graphics.
Maybe you could like send an email to the city of Newark and be like, hey, between 10 and 12:40.
That's actually Rutgers right there.
Okay. Well, I think in general, it's just the city's kind of
Loud. Yeah.
any city.
No, sorry. Yeah. Actually, I think I've always liked the windows open in this room, despite the noise, because it gets hot in here if you don't have them open too. But yeah. If I'm ever talking too quietly and it's not enough over the noise, just give me the thumbs up and I'll start shouting. Okay. So why? Wait, we're missing one. Whatever. It's recorded. We'll keep going. Okay, why randomization matters. We're good. Here's another reason why randomization matters is voting rates differ by household type, right? So here we're going to compute the voting proportion by sex and household size. So we're going to ask, do men and women vote in different rates depending on how big their household is? And so for household size, we have 1, 2, 3, 4, 5, 6, 7, and then 8 is our kind of top bracket. We're saying anything higher than 8 just gets counted as 8. So this is effectively a measure of how many people are in the household, usually how many kids are in the household, right? And so we're going to get voting proportion there. And we're going to plot out the voting rate by sex for household size. And what do we see going on here? People with big households, man, they vote, right? But the men vote way more than the women. We see a relatively clear pattern here. This is actually telling me that there's one man in this data set with a household size of 8 and like 2 women, and one voted and one didn't. This is actually just noise. But if the data were large enough and this were real, that would be concerning, right? But we do see a bit of a pattern here that single adults tend to vote at a pretty high rate, right? People with 3 and 4 size households, 5 size households tend not to vote as much in primaries because it's time consuming if you have kids at home, probably, right? And then people in larger household sizes do tend to vote more. I won't speculate on that, but we do see a bit of a pattern here. The scale's kind of thrown off because it goes up to 1 here, where the scale on this one went up to 0.4, right? So the 0 to 0.4 here is the full range. And basically that other graph is only this portion of it, right? So we can still see some differences in that range. And then this 8 is throwing us off, but that's fine. Anyway, this is to say that there are differences across groups, right? And so we want to average out those differences whenever possible. And sometimes we're going to know those things we should average across, sometimes we're not. Randomization ensures that we are effectively controlling for everything, controlling for every possible difference between the groups. Things we know, things we don't know, things we could know, things we could never know, right? Okay, certain kinds of people are more likely to vote in primaries than others. We note these differences between observed variables and our outcome, primary 2006. That's one thing we just did to show, like, yes, there are systematic differences between groups. We didn't measure very much here. We only had a handful of variables: household size, sex, age, measured as year of birth. What are some other variables that we can imagine might affect voting? Education level, income, proximity to polling place, exposure to campaign information, prior party identification, whether it was an incumbent in the primary or not, in the party that you identify with. So many things, right, could affect this. And we only measured 3. So I definitely want to rely on randomization to make my inferences rather than allowing this to be observational where I compare across groups based on these reported variables. So randomization, given a large enough N, ensures that treatment and control groups are identical across all observed and unobserved or unobservable differences prior to treatment. Okay, so that condition, statistically identical treatment and control groups, I know I'm just kind of like hammering this in at this point, is a necessary condition for causal inference. The treatment and control groups must be statistically identical to estimate a causal effect. That's called, for causal identification, to identify the causal effect for internal validity of the study, we must have statistically identical groups in our treatment and control. And that's true whether we're doing an experiment or an observational study. We must have statistically identical groups. So randomization is the most straightforward way to achieve this, but there are others, right? So if we can, randomization by definition gives us statistically identical groups, but there are other ways we can get there too. So let's talk about causal inference in observational data, which for the social sciences, unless we're in psychology, is most of the time how we're going to be working with data. We're going to be working with data that someone else collected for some other purpose, right? If we're doing criminal justice research, we may be working with administrative data from a police agency. We may be working with survey data about, I don't know, substance usage among adolescents. We may be working with sensor data on traffic patterns for pedestrians or cars at particular places. We may be working with atmospheric sensor data on air pollution. There's all kinds of things we could be working with that the data is collected from broad observations of a social group, and there's no direct intervention that's made that we're evaluating, right? We're just collecting the data. We may not even be collecting the data. The data may be collected by someone else, but we have systematic observations of something, and we'd like to learn something from it. So one example that we're going to work with here is with a study designed to estimate the impact of a minimum wage increase on employment levels. So in 1992, New Jersey raised its minimum wage from $4.25 to $5.05, and Pennsylvania did not. We would like to know if employment patterns across Pennsylvania and New Jersey systematically differed after the implementation of a minimum wage. Now, there's a lot of debate in economics and public policy about the impact of the minimum wage on employment and on average wages among the working poor. My opinion on the evidence is that it's relatively clear that the minimum wage boosts economic outcomes for the working poor. It's pretty clear, I think, at this point, but there's still some argument about whether that's true and how exactly that happens. We have a few measures here. The wage of a work, so what we're doing here is we're looking at fast food restaurants, which are minimum wage employers in these two locations. Actually, some of them are, some of them aren't, but we're looking at fast food employers in Pennsylvania. So what we're going to see is even among those who are maybe not at the minimum, does the raise in the minimum wage affect average wages? Does it affect proportion full-time, proportion part-time? So we can measure employment as how much are you paid, how many hours are you getting? And that's kind of two ways we can think about the impact of the minimum wage on employment at a particular fast food restaurant, right? Did the change in the minimum wage change how the managers and owners of these fast food restaurants paid their employees and how they assigned hours, right? That's the research question. Now, what do y'all think about comparing New Jersey and Pennsylvania? New Jersey passed a minimum wage law, Pennsylvania didn't. In this study, we're going to try and make the case that this is an exogenous change such that this is something the legislature did that has nothing to do with fast food employment per se. It's outside the system of fast food employment. And New Jersey and Pennsylvania, because they are neighbors with each other, are comparable. So we're going to make the case because they're right next to each other, that they're pretty close to each other, that we're going to treat them effectively. We're going to treat Pennsylvania as the counterfactual for New Jersey. New Jersey was exposed to the treatment, minimum wage went up. Pennsylvania was not exposed to the treatment, minimum wage did not go up. If we accept that these two cases are indistinguishable, except for the fact of this exogenous change, this outside of the system change, exogenous meaning it came from somewhere else, right? The minimum wage just changed. We can compare these two and treat them as if they would have followed the same trajectory with or without the minimum wage increase, right? That's the assumption. I'm not asking you to accept it, but that's the assumption we're going to make. That's the assumption required for working with this kind of observational data. Yeah.
When it's like, I don't have it, I just
No, you're fine.
So I don't really know, I can just keep it. But when you are doing that, when you're writing a paper, do you have to like make a case about
Yes.
it being, so you'd say like we controlled for all these things over, so it's like not really an assumption, it is based on like comparing the groups.
Yeah, well, I mean, it's still going to be an assumption, but you need to make the case about why that assumption is valid, right? That's discussing the internal validity of your study. The internal validity of your study hangs on these two cases being effectively identical, other than this exogenous change. It also depends on the change being exogenous. It depends on the change having nothing to do with fast food employment, which I think we might have a circumstance in which the conditions of fast food workers would in fact affect whether a legislature decides to change the minimum wage, right? The employment conditions in a state probably are impacting legislative decision-making on minimum wage law, right? And in that case, we actually have a big problem in that the cause of the minimum wage increase might actually have something to do with what was going on with New Jersey's fast food employment, right? And if that's the case, we can't identify a causal effect. But that's like technical details to be argued out at a high level. Right now, we're just going to assume that it works. Yeah.
They didn't control for any other factors.
We'll get there. We'll get there. But right now, our assumption is New Jersey and Pennsylvania are identical other than this exogenous change, outside the system change to minimum wage. And if we make that assumption, then Pennsylvania is our counterfactual, right? Okay, so let's look at the data, kind of work through what we have in here. We can see we've got a handful of variables: location, wage before, wage after. This is pre change in the law, post change in the law. Proportion of employees full-time before, proportion of employees full-time after, proportion of employees part-time before, proportion of employees part-time after. Okay, so for chains, these are the restaurant we have. We have Burger King, KFC, Roy's, and Wendy's. And then these are the location codes we're going to have because we do actually want to parse out different portions of New Jersey. And we're not including the full state of Pennsylvania here. We're including only that segment that is close to the border with New Jersey. The idea is that that region of eastern Pennsylvania that's right on the border of New Jersey should be indistinguishable from certain parts of New Jersey. The only difference between those two locations is that there's a border separating them. Right? The border is kind of treated to be arbitrary relative to the outcome that we're interested in, because people could hypothetically commute across the border to work, right? Okay, so we have Central Jersey, North Jersey, Pennsylvania, Shore Jersey, and South Jersey. And effectively here, we're going to argue that North Jersey and the Shore are different from Pennsylvania, right? Where we are, it's not quite the same as Eastern Pennsylvania. The Shore is not quite the same as Eastern Pennsylvania. But South Jersey and Central Jersey are pretty close to Eastern Pennsylvania. So maybe we'll stick those two in as comparison groups, and maybe we'll hold out like Newark and Patterson and, you know, the kind of the big cities that are in the New York City metro, right? And those are systematically different. Okay. So did the New Jersey minimum wage increase the wages paid to employees? First, let's group by location, right? Because effectively that's going to determine whether you're in the treatment or control group in our study, right? Location is a proxy for minimum wage exposure. Then we can compute the mean wage before and the mean wage after. So for Central Jersey, we see a 463 to 509 increase in wage, 463 to 509 in North Jersey, 464 to 507, 454 to 506, and then in Pennsylvania, 465 to 461. What does this table show us? That restaurants in New Jersey largely complied with the law when the minimum wage changed, right? That they followed the law. The wage went up to over 505, which is certainly what we would expect to see or hope to see after the passage of a change in the minimum wage. We saw no such change in Pennsylvania, which, if we believe this is a good counterfactual case, is starting to suggest that the minimum wage increased wages, which is kind of a like not especially surprising finding, right? Because that's what the law does. And assuming any people follow the law, this shows that New Jersey followed the law, right? And Pennsylvania didn't because they didn't have to, because it wasn't a law in their state. This doesn't really tell us much other than like the law had its intended effect on wages. Okay, but we can look at changes, right? So we can compute the mean wage before, the mean wage after. So I'm sorry, this is, oh, okay. What proportion of workers are at or above the 505 minimum wage before the minimum wage increase, and what proportion are at or below the minimum wage after the minimum wage increase? We're using a greater than or equal to achieve this, right? So this again is just another measure of compliance with the law. Central New Jersey, some employers are still not following the law for some reason. After it passes, we've got like 2% of employers who are still paying people below the minimum wage. But in these other places, we have full compliance. right? But obviously in Pennsylvania, the proportion of workers receiving less than 505 an hour is still, or the proportion of workers receiving more than 505 an hour is about 5% before and after, right? And notice this is actually like 6% and this is actually 4.5%. But again, we don't want to like split hairs over small differences, right? We want to talk in kind of general terms about what's going on. Call us about 5%, right? Measurement is always imprecise, right? Measurement is always imprecise. So we want to talk about kind of big differences. We don't necessarily want to get focused on small differences in statistics because measurement is always subject to error. Okay, so let's compute the proportion full-time before and after. So full-time, how many? So we might imagine that an increase in the minimum wage. Hey, they shut down. We just need to order rainstorms every time I teach. So get on making a weather control machine and our experience will be better. Okay, so we might imagine that, whatever. In the aftermath of a minimum wage increase, we might imagine that employers would choose to reduce hours, right? Would choose to cut hours as much as possible such that they don't have to pay as much, right? So we're going to ask, what proportion of employees are full-time before and after? So we'll divide full before by full before plus part before to get a total number of employees. Full and part-time gives us the total number of employees. So proportion full is full divided by full plus part. We go back and look at this, right? This Wendy's had 20 full-time employees and 20 part-time employees before. So we're going to do, so the ratio of full to all is going to be 0.5. 20 over 20 plus 20. Yeah. This one had 6 and 26, so it'll be 6 over 32 for this one. Let's compute those. And here's what we'll see. In Central Jersey, 0.31 before, 0.25 after. In North Jersey, 0.32 before, 0.375 after. Pennsylvania, 0.31, 0.272. So is anyone kind of seeing why I think this might be interesting already? Can you speak a little louder? Possibly, but we saw the same decrease in Central Jersey and Pennsylvania, which are the two cases that are arguably closest to each other. We saw a decrease in full-time employment, about 0.6, about 6 percentage points here, and about 5 percentage points, 4 percentage points here. So there might have been something going on in the economy in this place that pushed full-time employment down that wasn't the minimum wage, right? And that's something we want to pay attention to, right? Is there are trends that are outside of our system that are also going to affect our inferences, right? Things that have nothing to do with the minimum wage will also affect employment. And the reason we want control groups is so that we can say, oh, okay, in our control group, we have this decline in employment after this minimum wage passes, but the minimum wage had no impact here. We know that. And this is the most similar location. And we see that decline in employment, but just eyeballing this, we would be wrong to attribute this decline to the minimum wage law. At least that's like my thinking as I look at this table, right? That's the kind of thing you want to start like thinking like an applied statistician. That's the way you want to start thinking. It's like looking at these and like, what's the story that this table tells us? Yeah.
You didn't say that it was that the control that Pennsylvania rate was the opposite, but it did. There, like what? How does like someone who's analyzing this data know, like for this specific data set, like given how many like data points they have, and like what when something is significant? Like
we're not going to talk about significant yet.
Okay.
Significance coming at the end of the semester.
Got it.
We're just doing differences now. We do need to ask how certain am I about where this number is? How certain am I about where this number is? And do we think this is a meaningful difference? That's an important question, but we're not there yet. We're going to talk about standard deviations later today. And that's going to start us on our journey to uncertainty. Uncertainty is actually like the entirety of what statistics is about, right? But we're not there yet. Okay. So is this relatively clear, at least how I did this computation? Okay. Maybe the interpretation's still a little tough, but let's estimate the causal effect. And before we start subsetting the data based on region of New Jersey, let's just do Pennsylvania and not Pennsylvania. That's the simplest comparison. So we're going to filter. Control is PA. The proportion full-time is the average proportion full-time in Pennsylvania. Treatment is not Pennsylvania. That is everywhere in Jersey that got the minimum wage bump. And again, we'll compute the average proportion full-time. And we'll see that if we just compare all of New Jersey to our Pennsylvania locations, we see that if there's actually a 5-point jump in full-time employment after the implementation of the minimum wage in New Jersey. So based on, without subsetting regions, just Pennsylvania versus New Jersey, we see a positive effect of the minimum wage increase on proportion full-time employment, assuming that this identifies the causal effect, right? We're going to just like assume that away for now, pretend that this identifies the causal effect. We could definitely have debates about whether this does. Okay. So is this valid? Confounding can jeopardize causal inference. Confounding bias is when a third variable is associated with both the treatment and the outcome. This is called an endogenous variable. An endogenous variable is something that's associated with both exposure to treatment and the outcome itself. Something that's correlated with getting the treatment and with your value on the outcome. So some third variable that's associated with both things. That's a confounder, and that's called an endogenous variable. An exogenous variable, so here, let me just, now that we kind of have this terminology, is associated with treatment and outcome. And this is associated only with the outcome. An exogenous variable only affects the outcome. It does not affect exposure to treatment. An endogenous variable affects both treatment and exposure to treatment and the outcome. And if that still doesn't make a lot of sense, the more we work through this, the more sense it'll make. I don't expect this language to like click with you right away. This language is tough. Okay, but a confounding variable is a third variable that is associated with both the treatment and the outcome. And a causal system, as we mentioned earlier, can have dozens, hundreds, thousands of confounders, some of which we'll be able to observe, some of which we won't. Selection bias is when a unit chooses to participate in a treatment for reasons that are correlated with the outcome, right? So I choose to raise my minimum wage in New Jersey because my wages, I believe, are too low, right? I think the wages are too low for the cost of living in my region as a legislator, and I'm hearing from minimum wage workers that their wages are too low. I'm being lobbied by their, trade groups or their unions or whatever. So yeah, I'm going to raise the minimum wage. That's associated with the outcome. The outcome is, employment, right? Is employment stability for these workers. And so the value of that outcome is influencing my decision on passing a minimum wage. That's endogenous. That's a selection bias. I'm choosing to go through the treatment because of my value on the outcome. I'm choosing to seek medical treatment because I have cancer, right? I'm selecting into that group. Okay. So selection bias, confounding bias, two important things we need to keep in mind when we're evaluating the internal validity of a causal inference. That's a lot of stats language. But remember, we talked about external validity is like, does this generalize to other cases? Internal validity is, do we believe that we've estimated the sample average treatment effect for our research question?
what way would it compromise? That like a business owner is choosing to comply with the law.
I'm
And
listening,
in
sorry.
doing so, that impacts whether or not they would have more full-time employees anyway. Is that the?
No, the argument is more about why did New Jersey pass the law?
Okay.
Did New Jersey pass the law for reasons that have anything to do with employment conditions in the fast food industry? Right? In a way that's different from what was going on in Pennsylvania, right? So if New Jersey's starting conditions in the fast food industry were different from Pennsylvania's in ways that led the legislature to pass a law in New Jersey that did not pass in Pennsylvania, then we are not actually talking about equivalent groups, right? We're not talking about equivalent units at that point. New Jersey may have selected in to passing a minimum wage because, and in this case, our outcome might be proportion full-time employment, because they were concerned that fast food workers their working conditions were too precarious and they wanted to raise their wages. If legislators and the governor were concerned about fast food workers when they made this decision, then we have selection bias. So I'm just going to go ahead and say I don't actually believe we have internal validity in this study, and I think these kinds of studies often are kind of fragile when it comes to the assumptions that we have to make to believe that we've identified a causal effect. But they're done all the time, and it's important for us to understand them. And sometimes they can teach us things, right? There are cases where we truly do have some exogenous event occur to make two otherwise similar places experience something very different. A natural disaster is a great example of this, like an earthquake, right? Or various other kinds of weather events might randomly affect one area and not another, and then we can compare what happens across those. You've heard the term natural experiment before, I assume, right? A natural experiment is an exogenous event. An event that comes in from outside the system and changes things up, and then we can look at what happens. Like a pandemic. Yeah. And now whether we have like units exposed and units not exposed, that's the tougher part, right? Okay. So correlation is not equal to causation, right? You're going to hear this a lot, but we may see a correlation between the minimum wage increase and full-time employment. But unless we can meet the assumptions that there is no confounding bias and that there is no selection bias, unless we can meet these two assumptions, we cannot claim that the difference that we've computed is a causal effect, right? If there's confounding, if there's selection, all we have is correlation. We don't have causation. Correlation meaning two numbers are associated with each other. When one moves, the other also moves, but it's not necessarily a causal effect, meaning the movement in one variable is directly causing the movement in the other variable in a direct pathway, right? We'll talk about kind of causal systems and causal diagrams and stuff later, but okay. So ways to deal with confounding or selection is to randomize treatment. That's not always an option. We can't like randomize minimum wages across states, right? That's not how government works. When we can't do that, we might use statistical control. That is, we can do within subgroup analyses based on known confounder variables. Now we're at the question of control. If we can make the case that we've identified all possible confounders, and we can make the case that there's no selection bias, if and only if we can make those two arguments, then we can use statistical control, and we can say, let's compare the averages across subgroups, right? If that variable region, right, for example, might be impacting things, we think that maybe North Jersey is in the New York City metro, and so that's got like a really different economy than like the economy in Eastern PA and Central New Jersey. Maybe we want to control that out. Maybe we want to control region out. And maybe we want to compare across distinct subgroups. We'll talk so much more about control. If this doesn't click right away, that's okay. But when you hear control, I want you to think about comparing groups, not controlling out a variable. Think of it as we're comparing subgroups. We're basically taking average values for different groups and comparing those. That's what control is. It's just comparing across subgroups. So let's look at chain. Chain might be one thing. There might be different corporate policies at these restaurants that lead to differences that are independent of the state they're in, right? So it might be the case that like Burger King has corporate policies that impact Burger King across Pennsylvania and New Jersey that have nothing to do with the minimum wage law, right? So we can look at the distribution of restaurants across each region, right? So this is what proportion of the fast food restaurants in Central Jersey are Wendy's, what proportion are Burger King, what proportion are KFC, what proportion are Roy's, right? And we can kind of do that for each region just to look at like, okay, are they equally distributed? So are chains equally distributed across regions? When we look at these numbers, do we see that each region has similar distributions of chains of restaurants? Not really, right? In Central Jersey, we don't have very many Wendy's, but we do in Pennsylvania, right? There are fewer Burger Kings here than there are here. There's more KFCs here than there are here. Roy's, does that even exist anymore? I don't know, but right, we get the idea that there are some differences in which restaurants are in which locations. So that might be something important for us to think about. That was helpful. Okay. Maybe restaurant chain matters, so let's control for it. What we're going to do then is we're going to group by chain when we compute the mean for proportion full-time post, right? So maybe the restaurant chain has a policy about full-time employment that impacts full-time employment such that we want to effectively account for that when we're computing differences. Okay, so we'll first kind of take our control group in Pennsylvania, grouping by chain type, so grouping by restaurant and computing the proportion full-time in that control group. We'll do the same thing for treatment location not in PA, right? And then let's compute the difference in post minimum wage for full-time employment across New Jersey and Pennsylvania by type of restaurant. So now we're going to see if there's heterogeneity in the effect across restaurants. We're going to see if different restaurants saw different outcomes. So in Burger King, New Jersey compared to PA, right, we see about a 3-point increase in post-law full-time employment. KFC, we see about a 9-point increase. Roy's, we see about a 6-point increase. Wendy's, we see about a 1-point increase. So there are some differences there, but those differences could also be a function of region, right? So maybe region matters. So rather than looking at restaurant type here, we're going to look at location itself. So we're going to look at Pennsylvania versus every portion of New Jersey. So I'm going to take in my control, Pennsylvania, and in my treatment, not Pennsylvania, and then group by location. So I'm going to remove Pennsylvania first, and so then I'll only have my New Jersey regions. I'll group by those and compute my mean. So I'll get Central New Jersey, North New Jersey, Jersey Shore, South New Jersey. This is Pennsylvania, and I'm going to subtract these values from this value for each of those numbers. Right? So I can compute that by calling treatment effect, treatment prop FT post minus control prop FT post. I could do this tidyverse, but I'm doing it base here, right, with the $sign notation. And if I just subtract a single value from a vector, right, I can subtract that single value from each row of the vector. So in this case, I estimate an effect of -2 points in Central New Jersey, plus 10 points in North Jersey, plus 7 points in Shore, -3 points in South. So clearly different outcomes across New Jersey. This is effectively controlling, right? What we're doing is we're comparing across subgroups. That is the same thing as adding a control variable to a regression model. If this is actually identical to adding a control variable to a regression model. If you don't know what that means, that's okay. We'll get there, right? But this is the same idea. Okay. Now, so here we could describe this data as having, kind of potentially multiple levels of confounding, 2 of which we've measured, right? We've measured the chain, we've measured the location. So we could, in a rigorous study, compute the joint average of the chain by location and then difference those, right? That's going to get really messy really quickly in terms of what that table is going to look like, because we have 4 values for chain, 4 values for location in New Jersey. So that's a 16-row table, right? And that's going to get hard to look at. But we could imagine doing that. And if we were really interested in evaluating this effect, that would be the next step, right? Let's kind of talk about, so we've talked about kind of why, like the assumptions that would be required for this study to give us a true causal effect. And we've talked about ways that we can adjust for differences across units to try and get rid of confounding, right? Let's keep pushing this though. Sometimes you'll hear us talk about data that's either cross-sectional or in a time series. Longitudinal data is another way of saying time series data, which means we have repeated measurements of the same unit on the same variables over time. When we measure the same thing on the same unit over time. When I measure the wage at Wendy's before a minimum wage law passed, this one Wendy's, and the wage at that Wendy's after the minimum wage law passed. I have repeated measurements of the same thing at 2 time points. That's longitudinal data, right? If I have measurement of a child's height each year at their annual physical visit to the doctor, that's time series or longitudinal data on a child, right? But it's a repeated measurement of the same thing on the same individual or the same unit. I say unit because sometimes it's an individual person, sometimes it's a restaurant, sometimes it's a city, right? Our unit can be a lot of different things. That's longitudinal data. Cross-sectional data is one measurement of many units. So here, cross-section refers to time. We're just taking a broad cross-section. We're not measuring the same unit over and over again. We're just measuring one thing across lots of different units at only one time point. Panel data is when we put these 2 things together. Longitudinal data is measurement of the same variable on one unit over time. Cross-section data is measurement of lots of units. So panel data, sometimes called time series cross-section data, is repeated measurements of many units over the same variables over time. So we can put the cross-section and the longitudinal together to get repeated measurements on the same units, on the same variables at multiple time points. And that's actually what we have here. We have time series cross-section data because we have a lot of restaurants and we're measuring 2 time points for 2 different variables, right? Wages and proportion are 3 variables: proportion full-time, proportion part-time, and wages. So we have 3 variables that we're measuring at 2 time points across the same restaurants, but we have a lot of restaurants, right? Hundreds of restaurants in the data set. So right now, what we're working with is a special kind of data called panel data or time series cross-sectional data. This is a really common way that we collect data in the social sciences. It's when we repeat measurement on the same unit over time for lots of units, right? This is what a census is, right? For a level of geography, right? A census measures the population in a place every 10 years, right? And so we could call that a longitudinal data set for the population in a place, right? The place is the unit. The key advantages to panel data are the variables can differ both across units. So that is, we can have difference, we can have heterogeneity across units. That is, like, restaurants can just do different things, right? We can have lots of different kinds of restaurants that can all do different things, or states that do different things, right? But units can also change over time, right? Restaurants, so we can observe both differences in the population of restaurants and differences within those restaurants over time. So we get two kinds of variation. Yeah. No. Okay, sorry. So we get variation across units and variation within units. That's useful. So here's our before and after design visually. Here we have proportion full-time on the y-axis, and I'm calling time. I'm treating time continuously here, but this is pre and post, right? So time 1 is before the minimum wage. Time 2 is after the minimum wage. So here we can observe that in the red line is New Jersey. And you can see I have dots where we actually have observations. And then I'm just connecting those dots with the line. So in Pennsylvania, at time 1, we had a 31% of employees were full-time. At time 2, we're down to like 27% full-time. In New Jersey at time 1, we're at what? 29.5% full-time. After the minimum wage passes, we're at 32% full-time. Right, so this is the pre and post across our state units. This is a kind of longitudinal tracking of 2 units, New Jersey and Pennsylvania. Time 1, time 2, time 1, time 2. So what if we treated Pennsylvania, it's the counterfactual, and used information about its trend in employment to estimate the effect of New Jersey's minimum wage increase? So what do we see here? What if we treat Pennsylvania as what would have happened to New Jersey if they hadn't passed the minimum wage law? Effectively, what we're going to ask is, we're going to say they start in these 2 places, but let's superimpose the slope from Pennsylvania onto what happened in New Jersey as our counterfactual. It's easier to see. So, right, the assumption here is called parallel trends. The assumption is that the trend in the outcome over time would have been identical across units if the treatment had never been imposed. Okay, this is the parallel trends assumption. We're going to say that the trend that we observed in Pennsylvania is what we would have seen. The trend, meaning the slope of the line, is what we would have seen if the minimum wage did not pass in New Jersey, assuming all else is equal across those 2 units. Right? So that's visually what that looks like. We're going to start at the same point, but we're going to take the slope from our Pennsylvania line and make it parallel. We're going to make that trend parallel to the Pennsylvania trend. So we have the same intercept, but a different slope. So now, under this model, if we assume that the trends are parallel, our causal effect is not this minus this. It's this minus this. Our unobserved counterfactual. We use information about the trend from Pennsylvania to infer what the trend from New Jersey would have been if the minimum wage did not pass. I think this makes a lot more sense visually than it does kind of in words, but I'm also a visual person, so maybe whatever. But this is the basic assumption, right? We can see how these 2 trend lines become parallel, and the starting point for New Jersey remains the same. Right? That's the setup we're going to use for what's called the difference in difference model. Difference in differences model is going to take this parallel trends assumption to treat it as if we could have observed the counterfactual outcome for New Jersey, right? The place that we didn't actually observe no minimum wage increase. Okay, so mathematically, this is the difference in differences model, where Yij is the outcome group for group I and post-treatment time j. So we need a unit I and a time j. So for this model, we have to have 2 observation points, pre and post-treatment, right? And then we estimate this for minimally 2 groups. So the difference in difference estimator is Y bar, and Y bar just means the average of Y. So this means the average of Y in group 1 at time 1 minus the average of Y in group 1 at time 0. So this is the post-treatment group 1 minus pre-treatment group 1, right? The average of those 2 minus the average of group 2 post-treatment minus the average of group 2 post-treatment. And what this does is it effectively differences the slope, right? It takes the difference in values from our comparison state, Pennsylvania. And it takes the average and differences. It takes the average difference from the pre and post group. And so it's effectively removing the intercept and just getting us the slope, right? And here we're effectively removing the intercept and just getting the slope, and we're going to subtract the two, right? We're going to subtract the two to get what would have been the difference in outcome if the parallel trends assumption were true. Okay, so we're effectively asking what would have happened in New Jersey if the minimum wage had not passed. We're saying that this change in New Jersey is attributable to the minimum wage. So what would have happened if it hadn't occurred? Well, it should have been similar to Pennsylvania. Not just similar, it should have been identical to Pennsylvania. So let's move this line down and we'll compute it using this formula. This formula will give us this distance. Okay, so it's the average for unit 1 post-treatment minus pre-treatment minus the average for group 2 pre-treatment minus post-treatment. That's the difference in differences estimator. Okay, so let's compute it. So again, this is our pre and post for New Jersey and Pennsylvania. The DID is Y11 minus Y10 averages, right? Which we already have the averages here because these are proportions. So that's a mean, right? So Y11, so that's going to be post-treatment 0.32 for unit 1 minus pre-treatment 0.297. So we'll have DID equals 0.32 minus 0.29. Let's call it 0.3. Okay, minus what?
0.27.
0.27 minus what? 0.31. Okay. So minus 0.04, you get 0.02, right? So we subtract that, we get 0.06, right? So we get a causal effect of 0.06. That's our difference in differences estimate. It sounds complicated, but the math is actually not that hard. It's just subtraction again. But what we're doing is we're effectively removing out the intercepts of those lines and making this parallel trends assumption. That's the only thing we're doing.
So can you put in words what the 0.06 means?
0.06 here means that if New Jersey had not implemented the minimum wage law, we estimate that the minimum wage law increased full-time employment in New Jersey by 6 percentage points. So that's the simplest way we could put it. The minimum wage law in New Jersey increased full-time employment by 6 points. Let's kind of slow down. Does that click? What do you?
Yes. Well, I thought we were saying what it does not do.
Well, okay. We are guessing what it would have done if it did not occur. Our guess for what would have happened if we didn't get a minimum wage, based on what we observed from Pennsylvania, is that the minimum wage or the proportion full-time employment would have been like 0.26, right? This is what we think would have happened if reality did not happen, based on what we see in Pennsylvania, right? This is what actually did happen. When we subtract this dot from this dot, we get the 0.06. So we're assuming that if New Jersey had not passed the minimum wage, they would have had a proportion full-time employment rate of 0.26. Based on that assumption and what we observe, we get this estimate, 0.06. So we have to assume that this is what would have happened if New Jersey did not pass the minimum wage law for that number to be meaningful, right? That's the assumption that this hangs on, is this idea that what we observed in Pennsylvania is what would have happened in New Jersey without the minimum wage. Is that okay? And feel free to like slow me down and ask more questions on that. Okay, so there's our DID estimator, right? We call it an estimator when it's just a quantity based on a formula, right? This is the if we assume that the difference in differences model is valid, if we assume that the parallel trends assumption holds, this is the causal effect of the minimum wage law on full-time employment. It's positive, small and positive. Now, there's a lot of assumptions in there, right? So we're going to kind of leave it there for now. You can already imagine ways that we could make this more complex. We could make this more complex by controlling for region. We could make this more complex by controlling for chain, right? And even then, we would still have to ask the question, do we have no confounding? Do we have no selection bias, right? So there's a lot that goes into assuming that this is a valid estimate of the causal effect. And I don't want to suggest that we have truly estimated the causal effect. I think there are a lot of problems with internal validity in this study, but that's okay. We just want to kind of get the basic framework of the model down. Okay, I want to just kind of do an aside on descriptive statistics and a few things that we're going to use as we go forward. Should I check what time it is? Okay, cool. So we're going to do a bunch of things here where we summarize variables, where we compute a kind of summary statistic for a variable, and these are called descriptives usually, like a mean, right? Takes a vector, a list of values, and compresses it down to a single value, right? Because what a mean is going to do is it's going to take the sum of the vector and then divide by the number of observations within the vector. So we've already used min, we've used max, we've used median, we've used mean, we've used length, right? Quantiles are something that we've seen before, but I want to review briefly. The median is the 0.5 quantile of the data or the 50th percentile of the data. But quantiles are nice in that they're less sensitive to outliers than our other measures of central tendency, like the mean, right? Because the mean of like 0, 2, and a million, right, is going to be really high, but the median of 0, 2, and a million is going to be 2, right? So the median and these quantiles will move around a lot less if we have highly influential points that are very different from other points in the data set. So they can be really useful to help us summarize the distribution of a variable in ways that a measure like the standard deviation or the mean might not be as good for. So for one thing we can do is we can compute, say, the 25th percentile of the minimum wage before in our minimum wage data set. We're using the quantile function where we can specify the variable or the vector we want to compute our quantile of, and then a comma. And the second argument we're going to give it is which quantile we want. And it's going to be a value between 0 and 1, right? The quantile is expressed as a proportion. So we're going to say we want the 0.25 quantile. And that's defined as 25% of cases in this vector fall below this value, right? And in this case, it's 4.25. 25% of cases in the data are less than or equal to 4.25. And that is actually just that they're equal to 4.25 because that was the federal minimum wage, right? The 0.75 quantile tells us 75% of the values are less than or equal to 4.9875. Right, so we can change which quantile we get by changing this argument. We can also return lots of them at once by using the C function to concatenate, right? So we could get the 5th percentile, the 25th percentile, the median, the 75th percentile, and the 95th percentile all at once and return a vector of quantiles. And this actually gives us a really good sense of the distribution of the data, right? This confirms that 4.25 is the floor, right? And it tells us that 5.25 is about the ceiling. Right, there's really not many values there's no values underneath 4.25. Maybe there's 1 or 2, but the minimum is pretty darn close to 4.25. We could add 0 and 1 in here to get the minimum and maximum in there too if we wanted to. But this gives us a sense, the data doesn't have a lot of distribution, right? 90% of the data falls between 4.25 and 5.25. 95 minus 5 is 90, right? So 90% of the observations are within $1 of each other. There's not a lot of variation in wages at these minimum wage restaurants, at these fast food restaurants. There's not much variation in wages across places. The standard deviation, and again, this is just kind of a couple topics. I think you're going to use the standard deviation on the homework. I may have cut it, but I'll review it if we didn't. But we're going to use the standard deviation like crazy going forward. Anyway, a standard deviation is a measure of spread. So a standard deviation tells us how much variance there is in a variable. Within a vector, how different are numbers from each other? What it's actually computing is how different is each observation from the mean of the vector, and then it's computing an average statistic of difference from the mean. So what we're effectively asking is how different are observations from each other when we compute the standard deviation? How much variation is there in this vector? How different are values from each other? Now we can represent this as either SD. Sometimes you're going to see it represented as the population parameter sigma. This is lowercase sigma, right? So sigma, uppercase, we've seen for the summation, lowercase is this one. So lowercase sigma in statistics represents the population standard deviation. If it's just for the sample, we might describe it as SD. And if you're like, what the hell's the difference between a sample and a population? We'll keep coming back to that as we go forward. A sample is a subset of a population. So standard deviation provides a measure of how much each observation differs from the mean of the variable. In R, we can use the SD function to compute the standard deviation of a vector. So you can say SD of a variable, maybe with a summarize in tidyverse, or SD min wage $ prop FT before, right, in base. So the variance function, and in R, that's VAR, is the square of the standard deviation. So the standard deviation is the square root of the variance. The variance is the square of the standard deviation. Sometimes we're going to use one, sometimes we'll use the other. But this is how we compute the standard deviation. It's the average 1/n of the summation of xi minus x bar squared. Xi is every single individual observation in the data set. X bar is the average of the vector. And then we square the difference. So we subtract off the mean from each observation and square it, and then add up that sum of squares. So we sum those squares. Why would we square it, do you think? Say that again. Yes, to get an absolute number, so it's always positive, right? So squares ensure that if x is below x bar, we still get a positive number. Because we're not necessarily interested in having the differences below and the differences above cancel each other out. We want to sum up how much variation there is in this variable. So the square ensures that we get an absolute difference from the mean and not simply a directional difference, high or low. We're going to take the average of this, the average sum of the squares. So that's going to tell us what is the squared difference in the data. And if we remove the square root sign, we have the variance. When we take the square root of this, we have the standard deviation. You're going to work with this quantity over and over and over and over again. So I'm just introducing it here. I don't expect you to master it here. But the standard deviation is something we're going to see throughout our statistical journey. And again, variance is sigma squared. Okay, so let's compute the standard deviation on these. So can someone give me the mean for that first vector? So we have 5, 5.5, We just want to sum that over 10. Okay, thank you. So 5.125. So we'll say X bar equals 5.125. Okay, that's the first thing we need for our standard deviation formula. Remember, we can define the standard deviation as the square root of 1 over n times the sum of xi minus x bar squared. So now what we could do, so we take 5 minus 5.125 squared. So negative 0.125 squared plus 5.5 minus 5.125 squared. Right? Take that whole summation, divide it by n, which in this case is 10, and then take the square root of that. That would be the standard deviation for that vector. Or we could just feed R that vector and compute an SD. It'll do it for us, right? But in effect, what we're doing is we're differencing each of these values from the mean, squaring it to ensure it's positive, computing the average difference from the mean, and then taking the square root of that. It's not that complicated of a number, but it's a really, really important number that we're going to see over and over again. Okay, so why do we use standard deviations? There's a ton of reasons, but one reason is to standardize across different variables. We can think of a standard deviation as how different are observations from each other. Right? A standard deviation is a measure of how much spread is there in a variable. So how different are observations from each other? So we might want to ask, like, okay, is a 10-cent increase in the minimum wage meaningful when the minimum wage doesn't actually only varies a little bit across workers versus a context where the minimum wage varies a ton across workers? So 10 cents could mean very different things in different contexts. So maybe that absolute measure of difference isn't useful. Maybe we want a relative measure of difference. So standard deviation can be really useful with this. So how meaningful is a 10-point difference on a test, for example? So here what I'm doing is I'm simulating out a hypothetical test with a minimum score of 0 and a maximum score of 100. I want to simulate 50 scores on this test. This is R unit. This stands for random draws from a uniform variable. So this is drawing random numbers from a uniformly distributed random variable. You don't have to use this, but I just want you to understand what the code is. I'm going to do a lot of simulation stuff on the screen, but it's not actually stuff you're going to have to do, but it's how it gives us good examples, right? So test A could take on values between 0 and 100. And we're going to draw 50 scores, and they have equal probability of being any score in the range of between 0 and 100. Test B takes on values between 0 and 1,000, and I'm going to draw 50 of those as well. Okay. Oh, my plots didn't render. Sorry. I had some nice plots. I'll show you the plots. Okay. So that's the distribution of the two variables, right? Test A goes between 0 and 100. These are histograms, and this is one quick way to visualize the distribution of a variable. The height of the bar is equal to the number of observations between in each bucket of values. So in this case, there's 50 tests, I believe. There are 30 buckets, so it effectively kind of groups them into similar buckets and then has the height of the bar equal to the number of cases in each bucket. And we can see that these distributions look pretty similar. If we were to take 1,000,000 of them, they'd just be flat because there's equal probability across the distribution. Whatever, don't worry about that. But we can see this one goes from 0 to 100. This one goes from 0 to 1,000, right? Now, if my slides worked as they were supposed to, we could then look at the mean, right? So for these two sets, now, if we were to keep doing this over and over, they would fall exactly at 550, right? We can see the scale of the plot's a little different because we have a small number. So it's going to wiggle around 50. There's going to be a little variation around 50 for the average. That's called the sampling distribution of the mean, which we'll get to later. But there's some random error when we take a small sample, right?
That's called the sampling distribution. So here we can see where the mean for the population should fall, 550. Now let's look at that 10-point gap. Here's what a 10-point difference means on these two tests. So a 10-point difference on a test with a scale from 0 to 100 is a pretty big jump, right? A 10-point increase from the mean on a scale from 0 to 1,000 is a relatively small jump. That's not especially surprising. What about a 1 standard deviation jump? Okay, so next, what we're going to do is we're going to calculate the standard deviation of test A, which is 27.2, right? So on average, on test A, the scores are 27.2 different from the mean. On test B, do we think the standard deviation is going to be higher, lower, the same? Much higher, because the scale is an order of magnitude higher. It's 10 times higher, right? So the standard deviation is about 10 times higher. So instead of asking what is 50 plus 10 and 500 plus 10, we're going to ask what is 50 plus the standard deviation of test A, and what does 500 plus the standard deviation of test B look like? Look at that. Now we see that the jump is just about the same. So if we have heterogeneous units of measurement, that is, if our measures are on different scales, one way we can standardize to compare meaningful changes, to ask what is a meaningful change in test scores here? What is a meaningful change in test scores here? A standard deviation is a really convenient measure for a meaningful change. Right? How much variation is there in the data set? One standard deviation is a very convenient way to think about how much does one unit differ from the mean, right? What is the average difference in a unit? So this gives us a way to quickly standardize across different kinds of measurement. So if we're ever in a circumstance where we want to ask, is a change meaningful? So we asked, before, okay, so there was like a point, whatever, there's like a 0.2 increase in proportion full time. Well, is that substantively meaningful? Maybe we want to compare it to the standard deviation across restaurants, right? Maybe we want to compare that to how much difference is there across restaurants ordinarily to ask whether that's a meaningful difference. So that's about it for today. I have homework 4 posted on Slack. It will be more stuff like this. For this homework, you will be doing some more causal inference work. You're going to be using a data set I haven't shown you yet, but it's test scores. So it's an intervention for small classroom sizes to look at student test scores in elementary school over time. This is actually a very famous study. And the paper is available here if you wanted to read it. You don't have to. But what you're going to do, and I've given you in homework 4 how to read in the data, right? So you can go to that URL. That code is in the homework RMD already, and I'll post it on Slack. You can download the data just like that. And then we talked about case when last time. So this is how you will run case when to recode some variables. You might want to go back to last week's lecture. So when we talked about recoding, but we're going to recode some variables. Then we're going to look at comparisons across treated and untreated groups. We're going to compare them with the standard deviation of the test scores, and similar to the way I just showed you, to think about whether that's a meaningful difference. We're going to compare across subgroups, those who had different numbers of years in small classrooms. We're going to compare across racial groups, and then we're going to look at long-term effects by comparing high school scores. All of these should be relatively straightforward. There's no tricks here. The trick here is that the data is a little messy. There are missing values. So na.rm is going to be necessary for you to use when you're doing some of your computations. And this is going to be a bit of a challenge in terms of just doing the data wrangling. There's nothing here that I haven't shown you how to do. And again, I don't think there's anything too tricky here, but I I know I was slow in opening the Slack channel last time. I will go ahead and open the Slack channel right now today. And we will call it quits there.